and welcome back to our parallelism module. We've seen how SIMD processors work. So let's see what we need to know in order to program one of those units. And generally not independent processors, they're a part of a processor and they share the control unit with the scalar processor. So in order to program one of those units, we need to know which registers are available, what are their names, and which kind of instructions, vector instructions, are available over there. We're going to take SSC instructions as an example, but this can be generalized to pretty much any architecture that is out there. So let's say that we would like to do this. We would like to work on an array, and for each element in the array, we would like to find out what is the square root of that element in the array and write the results back in the memory. So if we are writing single instruction, single data type of a code, we will be working on each element of the array separately. First, for each element in the array, we would load f to the floating point register, perform the calculation, find what is the square root, and finally write the result from the register to the memory. In SIMD type of a code, and when we are working with essentially 4 wide SSC style of instructions that we find in Intel processors, we would take 4 elements from the array at a time. So we would load 4 members to the SSC register, then perform 4 square root operations in the same in one vector operation, and write the result from the register to memory. And that's it. This is how we got this speed up of essentially 4x. Let's take a look at a little bit more detailed example that would correspond to the assembly code that works with these SIMD units. So let's say that we would like in this example to add single precision floating point vectors. So these are single precision floating point vectors. They are 32 bits wide. So the computation that is to be performed, we are going to add 2 vectors, and each of these vectors has elements x, y, z, and w. The results go into the destination vector. So here is the code. There are 3 SSC instructions that are going to be executed, 2 moves and 1 add. So the first move moves the data from the memory to the XMM register in a way that it is memory aligned, packed, single precision. Memory aligned means that the data is aligned to 128-bit boundaries that correspond to the vectors here. So 4 of these suboperands x, y, z, and w are going to be 32 bits, forming a 128-bit vector. Pack single precision just basically means that they're packed as single precision operands within 128-bit vector. The second instruction is kind of interesting. Take a look at this one. We are not used to this in RISC-V. This exists in Intel's ISA. We are taking an operand from an address where the V2 resides and adding it in a vectorized way to the contents of XMM0. We can't do that in RISC-V, but in Intel's ISA we can do that. So RISC-V, remember, only has loads and stores for the operations with the memory. But here in Intel's assembly language, we can add the contents of a register to, or the contents of a memory location to the contents of a register, and store it in that same register, the original register XMM0. And finally, in the third instruction, we move the content of the XMM register to the memory location in the same way, aligned, packed, single precision. All right, that is it. The difference here that we do encounter are some of these a little bit more complicated addressing modes and a little bit more complicated instructions that may work where the operands may reside in the memory, but other than that, this assembly style is similar to what we are used to, at least in terms of granularity. Now, we generally don't want to really write the assembly code if we don't have to. So first we will rely on the compiler. And compilers, like GCC, do have access to these SSC instructions, but may not always perform in an optimal way. A common way how people will do this when they want to really get the ultimate performance is to use so-called intrinsics in C programming language. So intrinsics are C functions that essentially, instead of that one intrinsic command, replace it with an assembly instruction. So we are essentially inserting assembly instruction into the C code, and they're basically mapped one-to-one to their corresponding SSC instructions. So here, we can pick vector data type, which is M128, and then we can load and store operations. So this is memory load and memory store operations. They always start with this _m. That's how we'll find these intrinsics, and this is this will be moving, aligned, pack, double, and be represented as a double 64-bit instruction in the register. And then there are sample arithmetic instructions, which are _mm_add pd, which adds pack double, and then mul _mm_mul_pd multiplies pack double contents of those registers. That's it. All what you need to do now is to take a look at the manual for this extension of x86 and start writing C code that utilizes intrinsics such that you can get really good performance on vectors and matrices and stuff like that. We'll take a quick break. We'll take a look at an example after a break.